an exercise, and afterwards we'll take a break so we can continue clear-mindedly with chapter 5. So, Markov chains. A Markov chain, by definition, is a sequence of probability vectors and a stochastic transition matrix P such that this equation is satisfied. V of t, which is our probability vector at time t, is equal to P, which is our transition matrix, multiplied by another probability vector calculated at time t minus 1. Okay? Like I said, the vector V of t, which is a probability vector, describes the state of the Markov chain at time t. And I've also written here the definitions of stochastic and transition matrix, so maybe the actual definition is a little bit more complex. Let me tell you what we use Markov chains for. We use Markov chains in order to calculate the change of probabilities over time, depending on certain outcomes. So this is exactly what we're going to do. What we should keep in mind all the time when we're calculating, when we're doing exercises with Markov chains, is that we are actually calculating how probabilities change over time depending on different factors. So let's go into a little bit more theory, and then in order to understand how to work with Markov chains, we will perform a live example. So we say about a Markov chain that it can reach a steady state if there exists a probability vector C that can verify the equation P, which is our transition matrix, multiplied by this probability vector C, should be equal to the probability vector C, which means that a steady state represents a state in which we find our transition matrix so that the transition matrix multiplied by a probability vector will become the probability vector, which means that our equation basically has reached its limit. In order to find, for example, a steady state, we will solve the equation P, which is the transition matrix, minus I, which is the identity matrix. Okay, so we remember the matrix with a diagonal of ones. Everything multiplied by the probability vector C should be equal to 0, where 0 here does not represent a number, but the null vector. What is the null vector? Is a vector full of zeros. 0, 0, 0, that's a vector. It's a line, it's a column of zeros. Okay. Please pay attention that each stochastic matrix has such a steady state. So for every stochastic matrix, we can find a steady state. If a transition matrix P, however, is primitive, then the sequence, the V0, V1, V2, the sequence of probabilities, has only one steady state for which we say that it converges. Now, you're going to ask me, what is a primitive matrix? A primitive matrix is the transition matrix, which has the property that when it is powered to some power, it has absolutely no zero entries. What is a zero entry? It means that the numbers inside the matrix are different from 0. Uniqueness of the steady state. A Markov chain with primitive transition matrix P has a unique steady state C, and for each initial state V0, the sequence Vt converges to the steady state C. Why am I just throwing this information in your face and not really explaining it? Because this is a little bit of theory that you kind of have to memorize on your own, because there could be some theoretical questions regarding these Markov chains. Doesn't necessarily help us. All of this theory, of course, we'll understand it while we're practicing exercises. However, these definitions, as I've written them right here, are possible exam questions. So this is a slide that I would suggest you study a little bit more in depth, so you kind of know these definitions by heart. So now let's see how we actually work with the Markov chains, because there is no better preparation than actually preparing on an actual question. So we will work first on exercise 414, and if we have time, we will also do exercise 418. Or if you feel like you didn't understand really well, we can do that. So let's see. 414 here. So let's discuss a few of the elements that we have seen in our definition, but we didn't see how they actually look like. We have the Markov chain with a transition matrix. Our transition matrix is always going to be called P, and it represents a matrix full of probabilities. Each column represents the probability of an event happening, and you can see that by the fact that if you summate the numbers on columns, you will get 100% or exactly 1. 0.8 plus 0.2 is 1, 0.3 plus 0.7 is 1. Good. So this is our transition matrix, and it describes something. Our initial state V0, this is our vector, which tells us at the position in time 0, we have a probability 0.5 and 0.5 of something happening in regards to our Markov chain. We don't have too much information about this Markov chain. They're not relating it to anything market related or anything school related, so we can't really give meaning to these values. However, it doesn't change anything on how we work with them. So, given that transition matrix and the steady state and the V0 state 0.5, we have to compute V1, V2, and V3, and then we have to compute the steady states of our matrix P. I will turn back to the other slide in case you need to copy down the matrix. So this is our transition matrix and our position vector V, probability vector V. And now I'm going to switch to the whiteboard and start actually calculating this exercise together, okay? So we have our matrix P is equal to we have here 0.8, here 0.3. Here we have 0.2 and 0.7. And our vector V0, which will be equal to 0.505. This is information that the exercise has given me, so I haven't done anything yet. In part A, I have to find V1, V2, and V3. How do I find them? I know from the definition of the Markov chain that any chain of numbers Vt will be obtained by calculating the calculating the multiplication product of the transition matrix P by our V of T minus 1. So the term V that has been previous to V of T. Okay, perfect. Therefore, I can calculate V1 already. What do I need? I need P multiplied by V0. Because V0 is the number that exists before V1. How do I do this? I will start by writing down my two matrices. Like that. I have 0.8, 0.3, 0.2, and 0.7. In here, I have 0.5 and 0.5. And I simply have to do the calculus between the two, as if we were to create the product of matrices before, like we did yesterday. So let's do them together. But we all remember the product rule, right? So we have to multiply this line by every column of the second matrix. Because our second matrix is a vector, so it only has one column, we will multiply each line of the first matrix by the column of the vector. How? Initial term by initial term plus second term by second term. So it's going to be 0.8 multiplied by 0.5 plus 0.3 multiplied by 0.5. And the second term of our matrix will be 0.2 multiplied by 0.5 plus 0.7 multiplied by 0.5. And I will obtain if we take a calculator and do this calculus, we should obtain 0.55 and 0.45. And this is our probability vector at time 1. So 1 time after the initial value v0. What do we notice? We notice a change in percentages. Remember that the probability vectors v are probability vectors. It means that the summation of their elements should be equal to 1 all the time, the summation of their elements. Is this true? Yes, it is. 0.55 plus 0.45 will be 1. What do I notice, however? I notice a change that from the initial state v0 into change v1, there is an increase in the first percentage and a decrease in the second percentage. However, this increase and decrease is corresponding to one another because, again, the value of our probabilities together is equal to 1, which is perfect. It means we've done our job correctly. We move on to v2. v2 will be equal to, again, the transition matrix P multiplied by, this time, v1, because this is the state that has followed before v2. What is this going to be? Again, our transition matrix, which is going to be the same, this time multiplied by the vector v1. So our transition matrix doesn't change. It's 0.8, 0.3, 0.2, 0.7. What about our v1 vector? Our v1 vector has changed into this one that we just calculated here. So 0.55 and 0.45. Again, we do the calculus. And we will obtain 0.8 multiplied by 0.55 plus 0.3 multiplied by 0.45 and then 0.2 by 0.55, 0.2 multiplied by 0.55 plus 0.7 multiplied by 0.45. And if you do the calculus as well on your calculators, what you should obtain is the vector of position, the probability vector in the second position, so V2, which should be equal to 0.575 and 0.425. Again, how do I know I did a correct job? First of all, the probability has slightly changed. This change will become smaller and smaller, less and less insignificant as we reach the steady state of the matrix. Steady state meaning that the more we compute for V, V3, V4, V5, at some point, these percentages will change by so little that it will be insignificant. Therefore, we will say that we have reached the steady state of our Markov chain because these probabilities, these V vectors, are not changing anymore. The probabilities inside are slightly different from one another, but not really. So I'm speaking here about 0.0000000 something difference, something so insignificant we can't even see it on our calculators, okay? We would do the same thing for V3, but I don't want to waste time with another more calculation because it's not really relevant to what we're trying to do right now. However, it's really good practice for product of matrices. We are going to move on, however, to part B of our exercise, which asks us to find, one second. So we have to compute the steady states of our matrix P. In other words, what we have to find? We have to find a probability vector C so that our transition matrix P multiplied by C will be equal to C. And I told you, in order to solve this, we use the formula, the transition matrix P minus the identity matrix multiplied by our probability vector C should be equal to 0, which is going to be the null vector. This is how we solve for the steady states. So now I'm just going to go ahead and start writing down all of this information into a matrix. I think this is a little too big. Like that should be better. I'm going to draw all the corresponding matrices first. Okay, so my initial transition matrix remains the same, so that would be 0.8 and 0.3. 0.3 and 0.2, 0.7. This is my transition matrix. My identity matrix is 1, 0, 0, 1, because it's the identity matrix corresponding to a squared matrix of 2 by 2. Therefore, we have only 2 lines, 2 columns. So this is going to be transition minus identity multiplied by our probability vector C. Because we don't know anything about this probability vector C, we're just going to call its components C1 and C2. So we have to solve in order to find C1 and C2. It is going to be equal to the null vector 0, 0. Like that. This is what we have to solve. Therefore, we'll start calculating our matrices. We first do this subtraction, then we multiply this subtraction basically by our vector probability vector C1, C2. And it should be equal in the end to the null vector 0, 0. Okay. Inside the matrix, what do I have left? 0.8 minus 1 will be equal to minus 0.2. 0.3 minus 0 will be equal to 0.3. 0.2 minus 0 will be equal to 0.2. And 0.7 minus 1 will be equal to minus 0.3. And that's it. So I know that this matrix multiplied by this probability matrix C, represented by the values C1 and C2, should yield me the null vector 0, 0. What do? I will apply the row reduction procedure in order to obtain a full row of zeros. That's kind of the motivation you always want to look for in these when you're calculating the steady states. When you've reached the P minus I and you've calculated the matrix, you want to look for ways to obtain a line of zeros. That's what you should do. So we'll apply basically what? Row reduction. What type of row reduction will we apply? We will for example, we can do row 2 plus row 1. Why did I say plus row 1 and not minus? Because row 1 contains one negative here, which is going to turn my 0.2 into a 0. And here I have a positive, which will turn my negative 0.3 into a 0. This is why I have a plus. So what is left of my matrix will be minus 0.2 and 0.3, 0, 0, multiplied by C1, C2, should be equal to 0. Now I can turn this into a system. How do I turn it into a system? I will simply multiply this matrix by the vector, and I will obtain minus 0.2 multiplied by C1 plus 0.3 multiplied by C2 should be equal to 0. And then the second line of my equation, which I'm not going to write because it's going to yield 0 multiplied by C1, that's 0, plus 0 multiplied by C2, that's also 0, equal to 0. Therefore, I have 0 plus 0 is equal to 0. Of course, it's true. It doesn't make sense to write it again. Therefore, we will work on the first equation. And we know that minus 0.2 multiplied by C1 is equal to 0.3 multiplied by C2. Right now, I have absolutely no information that can guide me towards something, a relationship, something I can get out of my C1 and C2. Therefore, I will choose to move this negative term on the other side of the equation so it becomes positive. Therefore, I'm left with 0.3 multiplied by C2 will be equal to 0.2 multiplied by C1. Okay, that's great. I have come up to an equation from which I can deduct C1 or C2 from one another. What does this mean? It means that I will write either C2 or C1 as a function of the other term. Which one do I prefer doing? Let's say I want to write C1 is equal to. C1 will be equal to. When I take C1 out of this equation, I'm going to be left with 0.3 divided by 0.2 multiplied by C2. Therefore, I have written C1 as a function of C2. This is what it means. Great. This is enough for right now. I can also do the calculus 0.3 divided by 0.2, and I can write it in a easier form, let's say. Let's do 0.3 divided by 0.2, 1.5. C1 is equal to 1.5 C2. Like that. This is my final form. I'll write it again down up here. What can I do from here on in order to find C1 and C2? Well, I can put this information into my what's it called? Into my probability matrix C. How do I do this? I will write down that C, which is my probability matrix, will be equal to C1, which is going to be equal to 1.5 C2, because I've just deducted this from the equation, and C2. Like that. I can go one step further and take out C2 as a scalar product and be left with 1.5 and 1 multiplied by C2, because C2 is a number, will become my C matrix. But what property do I have to remember? That 1.5 plus 1 multiplied by C2 should yield 1 in the end. Why? Because C was a probability vector. And remember that I told you that the numbers inside a probability vector summated should yield a 1. What are the numbers inside the vector? 1.5 C2 plus C2, which is the same as writing 1.5 plus 1, everything multiplied by C2. What do I obtain? 2.5 multiplied by C2 should equal 1. Therefore, when I take out C2, I will obtain 1 divided by 2.5, and it should yield me 0.4. If I know C2, can I therefore find C1? Yes, of course I can. I know C1 is equal to 1.5 multiplied by C2, which is equal to 0.4. And this will become 0.6, which matches exactly the requirements I would have for my probability vector C, because C1 plus C2 should yield 1 totally. They do, and they should represent probabilities, which means that they should both be positive numbers smaller than 1. They are. Therefore, as a final answer, I will say that in order to find the steady states of my P, I had created all of this information, all of these algebraic calculus, and therefore the steady states of my matrix will be represented by the matrix C of C1 is 0.6 and C2 0.4. And these are the steady states. And this is how we calculate them. And this is all we need to do with Markov chains. How weird was this exercise? Did we all understand what I did? Could you guys follow through my explanations well enough? Yes, clear? Is this true for everybody? Yes? Okay. I'm so happy to hear, guys, because this is basically all that we need to do with Markov chains. This is the theory behind it. This is how we work with it. And if you agree with me, now that we've finished chapter 4, I think we should take a well-deserved 10-minute break. Everybody regroup at 10:50. We will address some last questions that if you guys have on chapter 4, so we can start chapter 5, which is not going to take us too long. So afterwards, we can practice some exercises from the past exam paper that I've seen are very, very interesting and I think are worth discussing. So if you all agree, we will meet back here again at 10:51, okay? Because the clock turned 41. All right?